Article 408.15 of the National Electrical Code, specifically the 2002 edition, mandates a maximum of 42 overcurrent devices within a single panel board. This regulation stems from a combination of safety, efficiency, and economic factors. Delving into the safety rationale, a high concentration of overcurrent devices, such as circuit breakers or fuses, elevates the probability of electrical hazards. Each device embodies a potential failure point. Should one device malfunction, it can cascade into a broader system failure, leaving multiple circuits without protection. This scenario significantly raises the risks of electrical fires and electrical shock incidents. Imagine a panel board crammed with numerous breakers. The sheer density complicates troubleshooting and maintenance procedures. Identifying the specific device responsible for an issue becomes a time-consuming and error-prone task. This difficulty extends to routine inspections and upgrades, potentially leading to overlooked problems and compromised safety. The cost factor is also significant. Each overcurrent device incurs individual procurement and installation expenses. Consolidating numerous circuits within a single panel board, while seemingly space-saving, ultimately escalates the overall project budget. The 42 device limit encourages a more distributed approach, potentially involving multiple smaller panel boards, which can optimize circuit management and cost effectiveness. To understand the implications of this limitation, consider several aspects of panel board design and application. Firstly, the physical size of a panel board is a constraint. Accommodating more than 42 overcurrent devices within a standard enclosure would necessitate a larger, more cumbersome unit. This can create installation challenges, especially in space-constrained environments. Secondly, the heat generated by multiple operating overcurrent devices is a concern. A densely packed panel board can experience elevated temperatures, potentially affecting the performance and lifespan of the devices. Proper ventilation and heat dissipation are critical, but these measures can be compromised when the device count exceeds the recommended limit. Thirdly, the complexity of wiring and cable management increases with the number of circuits. A panel board with numerous devices becomes a tangled web of wires, making it difficult to trace circuits, perform modifications, and ensure proper connections. This complexity can contribute to errors and increase the risk of electrical faults. To ensure compliance with Article 408.15, electrical designers and installers must carefully plan circuit layouts and panel board configurations. This involves accurately assessing the load requirements of each circuit and selecting the appropriate overcurrent devices. It also requires considering the available space, heat dissipation, and wiring complexity. In some cases, it may be necessary to use multiple panel boards to accommodate all of the required circuits. When selecting overcurrent devices, it is essential to choose products that meet applicable safety standards and are properly rated for the intended application. Factors such as the interrupting rating, voltage rating, and current rating must be carefully considered. It is also important to ensure that the devices are installed in accordance with the manufacturer's instructions and the National Electrical Code. Regular inspection and maintenance of panel boards are crucial for ensuring continued safety and reliability. This includes visually inspecting the devices for signs of damage or wear, testing the operation of the circuit breakers, and tightening connections as needed. Any problems that are identified should be promptly addressed by a qualified electrician. Let's delve deeper into the technical aspects. Overcurrent protection is a fundamental principle in electrical safety. Its primary purpose is to protect conductors and equipment from damage caused by excessive current flow. This excessive current can result from a variety of factors, including short circuits, overloads, and ground faults. Overcurrent devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. This interruption prevents overheating, insulation damage, and potentially catastrophic failures. The interrupting rating of an overcurrent device is a critical parameter. It specifies the maximum fault current that the device can safely interrupt without sustaining damage or creating a hazard. The interrupting rating must be sufficient to handle the available fault current at the point of installation. Failure to select a device with an adequate interrupting rating can lead to device failure, arc flash, and other dangerous consequences. The National Electrical Code provides detailed guidance on selecting overcurrent devices with appropriate interrupting ratings. This guidance takes into account factors such as the size of the conductors, the type of equipment being protected, and the available fault current. In addition to the interrupting rating, the voltage rating of an overcurrent device must also be considered. The voltage rating must be equal to or greater than the system voltage at the point of installation. Using a device with an insufficient voltage rating can lead to device failure and potentially dangerous conditions. The current rating of an overcurrent device determines the amount of current that the device can carry continuously without tripping. The current rating must be selected based on the ampacity of the conductors being protected. The ampacity of a conductor is the maximum current that the conductor can carry safely without exceeding its temperature rating. The National Electrical Code provides tables and guidelines for determining the ampacity of conductors based on factors such as the conductor size, insulation type, and installation conditions. When selecting overcurrent devices, it is important to consider the coordination between different devices in the system. Coordination refers to the selective tripping of overcurrent devices to minimize the extent of an outage. Ideally, only the overcurrent device closest to the fault should trip, leaving the rest of the system operational. Proper coordination requires careful selection and setting of overcurrent devices based on their time current characteristics. Time current characteristics describe the relationship between the amount of current flowing through a device and the time it takes for the device to trip. By coordinating the time current characteristics of different devices, it is possible to achieve selective tripping and minimize the impact of faults. The National Electrical Code provides guidance on coordinating overcurrent devices, including specific requirements for series-rated systems. Series-rated systems involve the use of two or more overcurrent devices in series, where the downstream device has a lower interrupting rating than the upstream device. In a series-rated system, the upstream device must be capable of protecting the downstream device during a fault. Ground fault protection is another important aspect of overcurrent protection. Ground faults occur when current flows from a live conductor to ground. Ground faults can be particularly dangerous because they can cause electrical shock and fires. Ground fault circuit interrupters, commonly known as ground fault circuit interrupters, are designed to detect ground faults and interrupt the flow of current before a dangerous condition develops. Ground fault circuit interrupters are required in many locations, including bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters are a relatively new type of overcurrent device that are designed to protect against arc faults. Arc faults are caused by unintentional arcing in electrical circuits. Arc faults can be caused by damaged insulation, loose connections, and other factors. Arc fault circuit interrupters are designed to detect arc faults and interrupt the flow of current before a fire can start. Arc fault circuit interrupters are now required in many new residential circuits. The National Electrical Code is a comprehensive set of standards for electrical wiring and equipment. It is updated every 3 years to reflect the latest advances in technology and safety practices. The National Electrical Code is adopted by most states and local jurisdictions in the United States. Compliance with the National Electrical Code is essential for ensuring the safety of electrical systems. Electrical inspections are typically conducted by local building departments to verify compliance with the National Electrical Code. Electrical inspectors review electrical plans and inspect electrical installations to ensure that they meet the requirements of the code. Failure to comply with the National Electrical Code can result in fines, penalties, and even the shutdown of electrical service. Understanding the principles of overcurrent protection and the requirements of the National Electrical Code is essential for anyone involved in the design, installation, or maintenance of electrical systems. This knowledge is critical for ensuring the safety and reliability of electrical systems and protecting people and property from electrical hazards. The 42 overcurrent device limit in Article 408.15 serves as a practical constraint, influencing panelboard selection and circuit distribution strategies. Firstly, consider the implications for residential electrical systems. While a typical modern home might not require 42 individual circuits, the increasing demand for electricity to power various appliances, electronic devices, and home automation systems necessitates careful planning. A large home with extensive lighting, multiple air conditioning units, and a dedicated home theater could easily approach this limit. In such cases, using multiple subpanels becomes a viable solution. Subpanels, fed from the main service panel, allow for a more decentralized approach to circuit distribution. This reduces the load in the main panel and simplifies wiring. Each subpanel acts as a separate distribution point, subject to the same 42 device limit. Secondly, let's examine commercial applications. In commercial buildings, the electrical demands are often significantly higher than in residential settings. Lighting systems, HVAC equipment, machinery, and various electronic devices all contribute to the overall load. A large office building, retail store, or industrial facility could easily require hundreds of circuits. In these environments, multiple panel boards and subpanels are essential. Careful planning is crucial to ensure that the load is distributed evenly across the various panels and that the 42 device limit is not exceeded. Furthermore, the physical placement of panel boards plays a vital role. Strategically locating panels closer to the loads they serve minimizes conductor lengths and reduces voltage drop. This improves efficiency and ensures that equipment receives adequate power. The selection of appropriate overcurrent devices is paramount. Circuit breakers are commonly used in panel boards for their convenience and resettable nature. Fuses, on the other hand, offer a reliable protection but require replacement after an overcurrent event. The choice between circuit breakers and fuses depends on the specific application, the level of protection required, and the maintenance considerations. Arc fault circuit interrupters and ground fault circuit interrupters provide enhanced protection against specific types of electrical faults. Arc fault circuit interrupters are designed to detect and interrupt arc faults, which are a common cause of electrical fires. Ground fault circuit interrupters are designed to detect and interrupt ground faults, which can cause electrical shock. These devices are often required in specific locations, such as bathrooms, kitchens, and outdoor areas. The National Electrical Code provides detailed requirements for the installation and use of arc fault circuit interrupters and ground fault circuit interrupters. Proper grounding is essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent device to trip and clear the fault. A properly grounded system minimizes the risk of electrical shock and equipment damage. The National Electrical Code specifies the requirements for grounding electrical systems, including the size and type of grounding conductors, the methods of grounding, and the bonding of metal enclosures. Regular maintenance of panel boards is crucial for ensuring their continued safety and reliability. This includes visual inspections, tightening connections, and testing overcurrent devices. Visual inspections can reveal signs of damage, overheating, or corrosion. Tightening connections ensures that the electrical connections are secure and prevents loose connections, which can cause overheating and arcing. Testing overcurrent devices verifies that they are operating properly and will trip when an overcurrent condition occurs. Any problems that are identified during maintenance should be promptly addressed by a qualified electrician. In summary, Article 408.15's 42 overcurrent device limit serves as a cornerstone for safe and efficient electrical distribution. It promotes a balanced approach that considers safety, ease of maintenance, and cost-effectiveness. By understanding the underlying reasons for this regulation and adhering to the National Electrical Code, electrical professionals can ensure the integrity and reliability of electrical systems in both residential and commercial settings. Let's further explore the practical implications of the 42 overcurrent device limit in various scenarios. Consider a small retail store with a limited electrical load. The store has lighting, point-of-sale systems, a small HVAC unit, and some refrigeration equipment. In this case, a single panel board with fewer than 42 overcurrent devices might be sufficient to meet the store's electrical needs. However, careful planning is still essential to ensure that the load is distributed evenly across the available circuits and that the appropriate overcurrent devices are selected. Now let's consider a larger office building with multiple tenants. Each tenant has their own electrical needs, including lighting, computers, and office equipment. In this case, a single panel board would not be sufficient to serve all of the tenants. Instead, multiple panel boards and subpanels would be required. Each tenant might have their own subpanel fed from a main panel board. This allows for individual metering and billing of electrical usage. The design of the electrical system must take into account the diversity of loads and the potential for future expansion. It is important to ensure that the panel boards are sized appropriately and that there is sufficient capacity to accommodate future electrical needs. In an industrial setting, the electrical demands are often even greater. Manufacturing plants, factories, and warehouses typically have heavy machinery, specialized equipment, and extensive lighting systems. These facilities often require multiple large panel boards and even switchgear to distribute power effectively. The electrical system must be designed to withstand the harsh environmental conditions and to provide reliable power to critical equipment. Safety is of paramount importance in industrial settings, and the electrical system must be designed and maintained to minimize the risk of electrical hazards. The 42 overcurrent device limit is just one aspect of a comprehensive electrical safety program. Other important elements include regular inspections, proper grounding, and the use of appropriate personal protective equipment. The National Electrical Code provides detailed guidance on electrical safety in industrial settings. In addition to the 42 overcurrent device limit, other factors can influence the selection and configuration of panel boards. These factors include the available space, the voltage and current requirements, and the type of equipment being served. The available space can limit the size and number of panel boards that can be installed. In space-constrained environments, it may be necessary to use smaller panel boards or to locate the panel boards remotely. The voltage and current requirements of the equipment being served will dictate the size and type of overcurrent devices that are required. Higher voltage and current requirements will necessitate larger panel boards and more robust overcurrent devices. The type of equipment being served can also influence the selection of panel boards. For example, sensitive electronic equipment may require dedicated circuits with surge protection. Critical equipment, such as emergency lighting and fire alarm systems, may require backup power sources. The design of the electrical system must take into account the specific needs of the equipment being served. The selection and installation of panel boards should always be performed by qualified electricians who are familiar with the National Electrical Code and local electrical codes. Improper installation can create safety hazards and can lead to equipment failure. Regular maintenance of panel boards is essential for ensuring their continued safety and reliability. This maintenance should be performed by qualified electricians on a regular basis. In conclusion, the 42 overcurrent device limit in Article 408.15 is a practical guideline that promotes safe and efficient electrical distribution. By understanding the reasons behind this limit and by following the requirements of the National Electrical Code, electrical professionals can ensure the integrity and reliability of electrical systems in a variety of settings. Furthermore, the continuous evolution of electrical technology necessitates ongoing education and training for electrical professionals. Staying abreast of the latest code updates, product innovations, and best practices is crucial for providing safer and efficient electrical services. The National Electrical Code is regularly updated to reflect the latest advancements in technology and safety standards. It is essential for electrical professionals to stay informed about these updates and to incorporate them into their work. Product innovations are constantly emerging in the electrical industry. These innovations can improve the performance, efficiency, and safety of electrical systems. It is important for electrical professionals to stay informed about these innovations and to evaluate their potential applications. Best practices for electrical design, installation, and maintenance are constantly evolving. It is important for electrical professionals to stay informed about these best practices and to implement them in their work. By embracing continuous learning and staying at the forefront of electrical technology, electrical professionals can ensure that they are providing the highest quality services to their clients.